let's talk about the logic of regression algorithm. Okay, we have already done this, but let's just revise and then we can get into the prediction part and all. So regression analysis, what we said is that, and we'll talk about simple linear. Simple is where you have only one input and one output. So this is your x-axis, this is your input. Input is also called as what? Yesterday we discussed, what is that called? Feature.
Yeah, yes, sir, yes, sir.
Okay, it's also called as feature.
Yes.
And what is this called as? Output or
Y.
input output. Feature, target. Okay, so this is called your feature data, this is your target data. So now, okay, on training, how training is done? So this is your x-axis and this is your y-axis. So you are doing this. Now, this is the data, the input data that we do, right? Training data, okay? Train data we are passing, X and Y. It's the job of this algorithm to find a best fit line, okay? Which will represent all this data. So best fit line is done in a way that if you find the distance, okay? If you find the distance between this line to this should give us 0. Net answer should be 0. Okay, this is, let's say, +5.
Yeah.
Okay, let's say this is +2. Okay, this will be -8.
Yeah.
Something like that. Okay, -3. So -6. If you add them all, it should be 0. That means the line is representing all the data points, and this is your regression line. Okay, so there are 3 types of distances that we need to talk about when we do these kind of problems. Okay, just a second, I'll open my notes. So when you're performing this, here the important thing is to find the distance. Is it not?
Yes, sir.
Okay, it is to find distance. 1 second. Okay, so there are basically 4 types of distance, the way you measure the distance. Okay, let's say measuring distance. Okay, so there are 4 types of distance, okay, that we measure here. Okay, or in okay, you see my screen? Okay, I'll find the notes and I'll update them in PDF in the same location.
Okay.
So you have Hamming distance, Euclidean distance, or Manhattan distance and Minkowski distance. Okay, most common is Euclidean distance. Okay, now see, the role of distance is very important. Okay, on all. So when you look at the algorithms, right, that day we discussed, if you take SVM, right, if you take SVM or you take linear regression, the whole concept is based on distance, right? Find the line which represents all the data. That means we have to find the distance between each point on the line in regression. In SVM also, we had to find the line and find the distance between point and the line, right? The support vector and the plane, right? So, okay. So how do we measure the distance? Okay. So, okay. Okay. So even in the KNN we discussed, right? Nearest neighbor. Who's the nearest neighbor? Right? There also a distance, we discussed about the distance to find the nearest neighbor. Correct? So it is used in multiple algorithm. Okay. So this Hamming distance, okay, is useful to measure your binary distance, okay, or when you have a when you have the distance measured in vector format. Okay, so here you have either 1 or 0, present or not present. Okay, it cannot be used when you have multiple values. Okay, So, we use Hamming distance in situations where you have binary vectors. Okay, that means you have yes, no kind of situation, right? So in this case, okay, the distance is given by this. For some I to n, okay, and you take the absolute value of v1 of I minus v2 of I. Simple. Okay, so this is one way. Okay, but the one that we prefer is called Euclidean distance, and this is what you would have done in your intermediate also. We find the square root, right? Square root of the sum of the square of the differences, right? So if you have 5,3 and 4,3, you will say 5 minus 4 whole square plus 4 minus 4 whole square, and then you do the square root, right? So let's say I have a point here. So this is 1, 2, 3, 4, 5. And this is again 1, 2, 3, 4, 5. Okay, 5.5. 5.5 is here, right? And 5.5, 3.2. X is 3, 2 is here, isn't it? I want to find the distance between these 2 points, right? So first you say 5 minus x-axis. This is 3, right? 5 minus 3 whole square plus 5 minus y is 5, y is 2. 5 minus 2 whole square. And you perform the square root of this. So 5 minus 3 is 2, 2 square is 4. 4 plus 3 square is 9. You get 13, square root of 13. This is the, the distance between this. If you measure, you can see. If you do it on graph paper and you do it, you will see this line is root of 13. That is what? Maybe 3 point something, isn't it? 3.4 or whatever, right? This is what you get. So this distance is 3.4. So this is how distance are calculated. Okay, Euclidean is the most common, and most of the time you use Euclidean. But if you have a binary, your 1 or 0, generally in the color, we talk about if it is present or not present, right? So we use, and so you can extend it to any dimensions. Okay, in this case we have only 2 dimensions. You can say third dimension, z1 minus z2 whole square, right? Plus, a2 minus a1 whole square, etc., etc. Okay, so this is your Euclidean distance. The third one is called Manhattan distance. Okay, so Manhattan distance is generally that Uber and Ola, they use this kind of distance to find your distance between you and your taxi, your location and your taxi location. Okay, so it is also called a taxi cab distance. Okay, and here it is on flat ground. Okay, because in Euclidean and even in the Hamming, it can be any dimension, isn't it? It can be in any dimension. But the way this is designed is like you're assuming that it's a flat ground, okay, and it's not in multiple direction. It can be 360 direction only, right? Okay, and also, okay, so here you have integer feature space. That's what it means. So it is again sum for 1 to n, sum of your v1i minus v2i. Okay, so in a way this is similar to Hamming, okay, but does not have multiple dimensions. Okay, so again you can calculate using simple method here. This is your sum of absolute value for E1 minus E2. Okay, so you are doing sum and you are getting this answer here. So here you need distance and time both, distance and direction both, right? So if you say that, okay, let's say a taxi is here, right? And the one person is standing here, another person is standing here. This distance is 3. This distance is 5. Okay, doesn't mean that the distance between these two will be 2. right? That's what it means, right? If I tell you from school to my home is 5 kilometer and from school to my friend's home is 3 kilometer. What is the distance between me, my home and my friend's home? It is, you don't know until unless you know direction,
Yeah, yeah, yes, sir.
right? You cannot say 5 minus 3, 2 kilometer, right? What if the, his house is other side? Okay, then it will be 5 plus 3, right? So that's what, okay, the is doing. Okay, and then you have Minosky. Minosky is another Euclidean based thing, and this is also very useful in our so here it either uses your Euclidean or Manhattan concept only. Okay, and as I said, right, I mean, of course I'll share this, and the mathematics formula is there, code is there, you can see how it is actually calculating, right? So maybe tomorrow let's do these calculations of these distances. You see what happens when we give different input, how the output is coming. Correct? Let's do this as a practice tomorrow. I'll share the
Yeah,
link
yeah.
with you. You can practice.
Yes, sir.
So measuring distance is important in most of our algorithms, right? Whether it's linear, it's SVM, even the K nearest is okay, and of course clustering also we do. Clustering we again distance we look at. So distance will tell you, okay, if the data is related or not. Okay, if the distance is less, that means data they are related. If one data can represent two values, that means both values are same, isn't it? So yeah, so internally these are called, so we don't have to call these distances. When we call regression itself will call these distances inbuilt to find the distances. Okay, we don't have to do this, but we need to know on what basis they calculate the distances. Okay, now coming back to our discussion. Okay, so we find the distances between line and the point, and the line represents the best fit line, or where the total distance, net distance, is minimum. Okay, that means if you draw any other line, the distance will only increase. Now, two things I said. One thing I said is net distance should be 0, right? Plus or minus. Second thing is, if you add them, absolute value, it should be minimum. Okay, if you take another line, okay, then it will not be minimum. Okay, this is the best possible line which will have total distance a minimum value. Clear? And you can extend this for any number of axes. So we have already multi-axis, right? This is simple linear regression problem, which is one, you have hours and marks. Okay, so this is what you get, and you draw. Okay, and this is the intercept value, this is your coefficient value. It means so since we have only one x, you'll get only one coefficient. If you have multiple x, you will get multiple coefficient, right? And how do you write the equation here? Y equal to mx plus c. So m is your coefficient, right? So 9.61 plus 4.3. Okay. Okay, and then you make the prediction dot predict. Okay, and you get the values. Okay, and we can of course plot this. And coming back to the evaluation, tell me what are these evaluation? What is MAE?
Mean absolute error, sir.
Correct. So how do you calculate?
As shown here, we have to first find out the difference between the actual value and the predicted value. Then they have to sum up all those values obtained and find the absolute value of that.
Yeah, mean absolute. So first,
Yes, sir.
so you go from right to left. Okay, mean absolute value. Find the value,
Yeah.
find the absolute difference, find mean. So mean of absolute differences.
Yeah.
Okay, mean squared error. So mean of squared value. So
Yes.
you're not doing absolute, but you're doing the square.
Yes.
Then
Yes,
okay, you get into root mean square error. Okay, so these are the important root mean square. RMSE is one important metric. Okay, and we have scalar. We have all done all these things, right? You can calculate. We do not have any formula for RMSE, so you have to manually take MSE and find a square root of it.
yeah, that another matrix is there, no sir. ML underscore matrix or something. If I have imported that, I was able to do that.
Correct. But we're talking about sklearn only, right? So
yes, sir. Yes, sir.
use sklearn stuff only, right? There are multiple things, correct?
Yeah.
Right. So last time we did ML underscore, right? So yes,
Yes, sir.
that has it. Yeah. Okay. So we're talking about one, which can do everything, right? Okay. 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 So this is another method, OLS. Okay. OLS gives a lot more information. Okay. So now what we'll do is we'll look at this value OLS. What's the output of OLS? Okay, and we will run it and see. I mean, it's very simple. You just say OLS of x dot y dot x. Y is your output target variable. X is your feature set of values, right? So whether you say x train and y train, or you say x test or y test, but you say OLS of y comma x fit summary, and it will give you this all statistics. These statistics are important, and we need to spend time to understand each of these. This is the statistics behind your machine learning. Okay. Okay. So let's go one by one. Number of dependent variable. Not number, sorry, it's not number here. Dependent variable. What is dependent variable? Y.
Output. Yes,
Y,
sir.
right? If you put Y train, it will be Y train. If you put Y test, of course you don't put Y test. Y test is prediction, right? It will be Y train. Model, we are running OLS. Okay. Method, least square. Least square method is same as your Euclidean distance. Okay. Euclidean distance is called least square in your in sklearn language, machine learning language. Okay? Least square means we are following Euclidean distance. Everything, only this one has square, right? None of them will have square. Date, on which date I created this, when I ran it, at what time I ran it. Okay. Number of observations. Okay. Number of observations is number of rows that data has. Okay. Degree of freedom of residual. Degree of freedom is generally your x minus 1. Okay. So 32 32 minus 2, right? So 32 minus your 1 for target variable, right? And we have only one target variable, right? It's called one population problem. Okay, it's a one population problem. So 1 and then minus 1. That's the formula. Okay. Okay. Then degree of freedom is 1. Okay, because we have one population. Okay, so this is it. Now R squared value and adjusted R squared value. R squared value, adjusted R squared values are another metric just like RMSE. Okay, it tells you how well we have performed according to the average, basically. Okay, so we have here, let's do that, and then we'll come back and talk about it. Because we have to calculate R square also from now on. Okay, it's towards the end that I'm talking about it. It's in the last. Okay. This is your SVM for regression, right? So it is down only. Okay. Okay. Yes. Here. Okay. So this is the R square value. Okay. Or no, this is coefficient of regression. Okay. R square is this. R square is 1 minus, okay, SS residual, okay, and divided by total residual. Okay. SS residual is the distance, total distance. You can see distance is calculated here. Sum of the distances between each point and the regression line. Okay. So if I have to do this, okay. Okay, let's say okay, so this is your regression line, isn't it?
Yes, sir.
This is regression line. Now we'll draw a average line. So if you take the values of all of these, okay, so average line probably will come somewhere here, correct? This is average line. Somewhere here your average line will come. Okay. Now we measure the distance between line and this point. Okay, so you measure, okay, these distances as well. So you are measuring, same points are same. Okay, if we had not performed regression, we would have gone with average value. That's what we do, right? We discussed this before. So you find the distance between point and the average line, and you do the total. That is called your sum total. Sum, or SS stands for squared. Okay, it is called sum error. Okay, sum error. Okay, so your sum error, there is a word, S equivalent word for error. I'm looking for that. Deviation. Okay, we'll come back to it, doesn't matter. So we find, so now tell me, the error will be higher, or the value, okay? So the sum, the average of the sum of the value, sum of the total distance will be higher for a average line or for a regression line. If I add all the distances with respect to average line and with respect to regression line,
Average line, sir.
Average line will have the higher value, right?
Yeah,
by
regression
definition
line, it's almost zero. Like it should be zero.
No, it never be zero. Some absolute. I'm not talking about the. It is absolute distance I'm talking about.
Okay, okay. It will be higher with respect to average line only.
Yeah. See, if you take direction plus and minus, it will be negative. We saw that in the example. We
Yes,
created
sir.
10 columns and we did right. Always will be zero. Okay. So it will be zero only. When you are saying that line is going through, it will be zero. But by definition, regression says that that line is the one that is the lowest value. By definition only we are saying regression is a regression line which will have the total value zero. If you have another line which has that value less than this, then that becomes regression. So in this case, if let's say average, let's say for somehow, if average line, okay, if average line is giving you the minimum value, then your regression line is the average line only, right? By definition only we are saying that. That's how we are able to find regression line. Regression line means there is no other value which can give you the minimum sum of the distance between that line and the point. So obviously, this distance will be less. Let's say this distance is 5, and then the distance will be 8, right? So the values will be between 0 and 1 only. So your R square value will be, but yes. So what it does is, it does R square is, what is the formula you said? 1 minus. Okay. So 1 minus. Okay. So if you get, let's say 0.3 and you say 1 minus, it becomes 0.7. So why are we doing 1 minus? We are doing 1 minus to increase the magnitude. See, error is 0.1, that means accuracy is 0.9. 100 minus error will give you accuracy, isn't it?
Yeah.
So that's what I'm doing, 1 minus. 1 minus saying that, okay, if you see the lower value is not seen as positive, right? To make it a higher value, I'm saying 1 minus. Okay. At worst, what it can be? Worst is that your regression line and the average line is same. That is the worst thing that can happen. So in that case, it will be 8 by 8, which is 1. So 1 minus 1, 0. So that's what the minimum value the R square can take is 0. R square cannot take a value less than 0.
Because it is already squared, no, sir.
Okay, it has nothing to do with squared. Okay, now the reason why, okay, so if you see this, you know, you'll see the calculation why it is called R square. Okay, we start with correlation and covariance and then we arrive at R square. So yes, in a way we are doing R square there, but you see here, okay, we are not doing R square. Okay, there's nothing called R square here, right? So sometimes, okay, sometimes you might get negative values also. What it means is you have not done a good job. That means your regression is performing even poorer than average line, right? So practically speaking, you can get. Okay, that means when you do a very good bad job, when you close your eyes and you do work,
okay,
you know, you can get right.
Yeah.
But yes, but you know, we shouldn't get. So okay, so this is called R square. Now R square assumes there is only one factor, there is only one X. If you keep on increasing X, then the value will also change. That's called adjusted R square. So adjusted R square is 1 minus R square into n minus 1 by n minus p minus 1. N is your number of regressors and n is the size, sample size that you have. So here a regression and sample size will also play a role. So generally, if you see, adjusted R square will be slightly less than adjusted R square. Sorry, R square. And adjusted R square doesn't make sense when you have only one parameter or only one feature. So in this case that we are looking at, okay, where did we go? We came long way down. Okay. So in this case that we were doing, okay, so here adjusted R square is not at all important for us because we are looking at only one target variable. This becomes important in the example that we did where we have multiple you know, the input values, right? We had profit, we had the marketing spend, advertising spend, right? So there adjusted R square will be important. And adjusted R square will be slightly less than your R square. So it is taking into account the multiple factors. Okay. So this is adjusted R square. We'll stop here, okay?